Today we will learn the chapter 7. Chapter 7 title is the Linkage and Recombination and Eukaryotic gene mapping. Chapter 7 is composed of 5 subtitles. First and second is linked gene, and third is the 3-point test courses, and also fourth is how to make the physical mapping method, and also finally we will learn the recombination rate exhibit extensive variation. In this slide, we will see that the pattern baldness, the style of the baldness, there are several patterns of the baldness. Baldness is a hereditary trait, and recent research demonstrates that a gene for pattern baldness is linked to the genetic marker located on the X chromosome. So the gene for the pattern baldness is located in the X chromosome, but the gene is also linked to another genetic marker located on the X chromosome. So we will see the details in later. Okay. So in this slide, we will learn the first subject: linked genes do not assert independently. Before we go further, we have to check the principle of segregation again, and also principle of independent assessment. So, principle of segregation means that alleles separate during the meiosis. For example, so this is we already learned the principle of segregation in chapter 3. So we did monohybrid crosses. Monohybrid crosses means that cross between two parents that differ or only a single characteristics. So everything is the same except for the shape. One is homozygous round, and the other is homozygous is wrinkled seed. So, but one characteristic is encoded by two genetic factors, two alleles. One is large RR, the other is small rr. So in F1 generation, so in F1 plant, all of the phenotype is one parent, all of phenotype is round. At that, we did self-fertilization. So the F2 ratio is we can always have a 3:1 ratio. Round is 3 and wrinkled is 1. The reason why we can get 3:1 ratio is that so large R, small r, in this is F1 generation. These two factors are separate when gametes are formed. This large R is separate, it becomes large R, and small r becomes small r, and large R did large R, small r go to the here, except that they did the crosses with each other. So we can get 3:1 ratio. This is the principle of segregation. Alleles, large R, small r, separate during the meiosis. So in this slide, we will check the principle of independent assessment again. In chapter 3, we already learned that principle of independent assessment means that alleles at one locus sort independently from allele and another locus. Because this is the principle of independent assessment is very related to meiosis. So for example, genes including the shape is located in the different chromosome compared to the genes which is involved in the color. So genes located on different chromosome will sort independently. So this is the meiosis. So during the meiosis one, the random, for example, the gene, this is one example, genes which encode the shape is located in this chromosome, very big chromosome, and also genes encode the color is located in a small chromosome like this. and usually the metaphase 1, so usually the random alignment of homologous pairs of chromosome along the metaphase plate, that during the anaphase 1, and also it happens separation of homologous chromosome pairs like this. So the principle of independent assortment means that genes at one locus are sort independently from the allele at another locus. So this is principle of independent assortment. That's why the ratio in F2 generation, the ratio is 9:3 3:1. In this slide, we will learn the new concept, recombination. So let's start from the dihybrid crosses. So in parent generation, the one parent genotype is large AA, large BB. How about the other parent genotype is small AA, small BB? When they make the gamete from these parents, they will have the large A, large B gamete, and also from these parents, the gamete will have small a, small b. So after fertilization, the F1 generation, they will have the large A, large B, small b. So okay, this is the F1 generation. When they make their gamete, okay, when they make the gamete, the allele is sort independently. So one gamete, they will have the large A, large B, and also small a, small b. So this genotype is we can see in the parent generation. So these two gamete, we can say that original combination of allele, non-recombinant gamete, because we can see this gamete in the parent generation. Another combination is that large A, small b, small a, large b. So in this combination, we cannot see in the parent generation. So recombination means that F1 progeny reproduce the combination of allele in the gamete which differ from the combination in the gamete from its parents. So this gamete is different from the combination in the gamete from its parents. So, and also recombination means that sort the allele into new combinations. So it means that large A, small b, and small a, large b it means that sorting of allele into new combination. So this is the recombination. The conclusion was that through recombination, gamete contains new combination of alleles. So this is the recombination. In this slide, we will see the new concept, the linked gene. Linked gene means that gene 1 and gene 2 is located close together on the same chromosome. So this is a linked gene. How about the not linked gene? So previously we learned that gene 1 and gene 2 is located in another chromosome. But in the linked gene cases, usually the travel together, gene 1 and gene 2 is the travel together because they are located in the same chromosome, finally eventually arriving at the same gamete. How about this one? For example, the gene A and gene B is located in different chromosomes, so they do not travel together because they usually do the sort independently. For example, but the linked gene, because they are travel together, they are not expected to sort independently. So this is the linked gene, and this is the not linked gene. So we have to divide it by two cases. One is a linked gene, the other is not linked gene. Even though they have the same genotype, we have to think about the two cases, linked and not linked. This slide we will see the cross with linkage. Previously, all of our crosses with non-linkage. For example, the gene which encodes the shape and the gene which encodes the color is located in the different chromosome. So it means that each gene is asserted independently. In the F2 generation, we have 9:3 to 3:1 ratio. But how about in these cases? The gene for flower color and also gene for pollen shape. For example, in these cases, this is parent generation. The parent is the homozygous strain. One parent is purple flower and the long pollen. The other parent is the red flowers and the round pollen. So after crosses in F1 generation, we have the purple flower and the long pollen. The phenotype is nearly similar to the crosses with non-linkage. But when we do the self-fertilization, this is F2 generation. In F2 generation, we have this is the progeny number. One is 284 and 21 and 55. In F2 generation, the ratio is not 9:3 to 3:1. What happens? So it means that crosses with non-linkage, the ratio is always 9:3 to 3:1. If the ratio is not 9:3 to 3:1, it means that this crosses with linkage. It means that the gene which encodes for flower color and the gene which encodes for pollen shape is located in the same chromosome. Okay, so in the linkage, the complete linkage means that complete linkage, the gene A and gene B is located in the same chromosome, and complete linkage lead to non-recombinant gamete and non-recombinant progeny. So how about in these cases? In F2 generation, we have the non-recombinant progeny, purple and long shape, and also red and round pollen. But we also have the recombinant gamete, recombinant progeny like this. For example, purple and round pollen and red and long shape. It means that crossing over is happen. So we will see the detail in the next slide. So crossing over with the linked gene lead to recombinant gamete and recombinant progeny. So we will see the detail in the next slide. In this slide, we'll see some details in crossing over. So as I mentioned earlier, linked gene segregate as a unit and are therefore inherited together. But usually during the meiosis 1, crossing over happens. So crossing over leads to recombination. So after crossing over occurs between two normally linked loci, after that they will assert independently. So this is the crossing over. Crossing over happens during the meiosis 1. It can lead to recombination. In this slide is the test crosses to demonstrate whether two gene loci are normally linked or not. There will be two cases if they are two genes when they are gene is complete linkage. They will through the test crosses they will have this kind of the phenotype, and also if they show the no linkage, they will have the this kind of phenotype like this. Okay, let's start from the first. So this is the heterozygous, which is they have normal leaves and tall, but they are heterozygote. But two gene is when the two gene is linked to each other, okay. But the phenotype is they are normal leaves means that, and also another one is the mottled. Mottled means that Olukkan leaves, and also dwarf. Size is very short. But this is the heterozygote. But normal leaves is dominant than the mottled leaves, and the tall size is also dominant than the dwarf size. Okay, even though they are heterozygote, they will have the normal leaves and tall shape. So test crosses means that to cross with the homozygous recessive one. Okay, so if two genes is linked to each other, so they will make the gamete 1:2 ratio. They will have the large M, large D, and also 1:2 ratio, small m, small d. So finally, they will make the non-recombinant gamete. For example, in this one, they will make a small m, small d. So finally, after crosses, they will have normal leaves and tall shape. And also another one is that they will have the mottled leaves and the dwarf shape. So all of them, they will show that non-recombinant progeny. So they will show that non-recombinant progeny, because this is normal leaves and tall and mottled leaves and dwarf, and all of progeny show that non-recombinant progeny. So this is the complete linkage. The ratio is the 1:1. So complete linkage shows that all non-recombinant progeny are produced. Another case is the no linkage. For example, if the gene and M and D is located in the different chromosome, okay? So this is also test crosses. They cross with the normal leaves and the tall shape, and with the mottled leaves and dwarf shape. So this is heterozygote. So for example, if the genes are unlinked, for example, they will make the non-recombinant gamete, and also they will make the recombinant gamete. So after fertilizations, we will have the non-recombinant progeny and the recombinant progeny like this. So conclusion is that without independent assessment, half the progeny are recombinant and half the progeny are not. So half the progeny is the normal leaves and dwarf, and the mottled leaves and tall. This is the recombinant progeny. Half of them is the normal leaves and tall, and mottled leaves and dwarf. So if there is no linkage, means that the progeny, the ratio between the non-recombinant progeny and the recombinant progeny is 1:1. So this is another test crosses to demonstrate whether two gene loci are normally linked or not. Okay. In this slide, we will learn the concept of the crossover again. Previously, we learned that crossover related to recombination. Okay. For example, gene A and gene B is located in the same chromosome. They are linked each other. Okay. When there is no crossing over, and this case is there is no crossing over, and this case is there is the crossing over happens. Okay. If there is no crossing over, so this is the prophase 1 status, homologous and homologous chromosome pairs, they are they pair to each other. So one chromosome, they have large A, large B, and large A, large B. And the other homologous chromosome has small a, small b, small a, small b. So if there is no crossing over takes place after they finish meiosis 2, so each gamete receives a non-recombinant chromosome with an original combination of the alleles. For example, this is large A, large B is the original combination of allele, and small a, small b is also original combination of allele. So okay, if the single crossing over happens during the prophase 1, so this is prophase 1, and single crossing over happens between the two of the prochromatid. So usually the single crossing over takes place between only two of the prochromatid. Okay, so at that gamete, half of the resulting gamete will have the unchanged chromosome. We call it as a non-recombinant. And half will have a recombinant chromosome like this, small large a, small b, small a, large b. This is a recombinant gamete. So once again, when single crossover happens, usually single crossover takes place between only two of prochromatid, and gamete received half of them is the non-recombinant and half of them have the recombinant gamete like this. Okay. In this slide, we will learn how to calculate recombination frequency. For example, the gene which encodes the leaves color is the located gene, and also the gene which encodes the height of the plant is they are linked each other. Okay, so we did a test crosses, and this one is the phenotype is normal leaves and tall, but they are heterozygote. So when they make the gamete during the gamete formation, if there is no crossing over, so we will have the 50% we will have the large M, large D, and 50% we will have small m and small d like this. So when the crossing over happens, 50% will show that non-recombinant and 50% will show that recombinant. So the genotype will be like this. One is the recombinant, non-recombinant, one will be the recombinant like this. After that, we did test crosses, and also we have the progeny, the number is like this. So based on this number, we will see that with the linked gene, N and D, they are linked gene, they are linked, and also sometimes the crossing over happens. Usually this is the normal leaves and tall, this is a non-recombinant progeny, and the mottled leaves and dwarf, this is also non-recombinant progeny. Usually in this case is non-recombinant progeny is predominate. So the recombination frequency means that number of recombinant progeny. So this is the recombinant progeny number 8 plus 7 per total number of progeny. Total number is 55 and 53, and 8 plus 7 multiplied 100% means that based on this number, the recombination frequency is 12.20%. So this is how we calculate the recombination frequency. In this slide, we will see another concept in the allele in coupling configuration. And next slide, we will also learn the allele in repulsion configuration. So gene is P and B is they are linked to each other, and between P and B, crossing over happens. But we have to know some concept allele in coupling configuration and allele in repulsion configuration. Okay, let's start from the allele in coupling configuration. We call it as cis configuration. So cis configuration means that one chromosome contains both wild type allele. Wild type means that this is the fruit flies. If they have the green thorax, this is the wild type. And also this is a puparium. Puparium means that the hardened rubber skin that encloses the purple. In Korean, we call it as 번데기 껍질. Okay, the green thorax is wild type, and brown puparium is also wild type. So they are the heterozygous because the one chromosome has both wild type, and the other chromosome is they have both mutant alleles. So when they make the gamete during the gamete formation, so this is the non-recombinant gamete, which has P plus, B plus, and P and B. But the other one will be the recombinant gamete, which has the P plus and B and P, B plus. So after fertilization, so this will become the non-recombinant progeny, and this will become the recombinant progeny. So usually the non-recombinant progeny is the predominated. Okay. So green thorax and brown puparium. And also another one has the purple thorax and black puparium. So they are non-recombinant progeny. They will also have the recombinant progeny as the green thorax, but they have the black puparium. Another one is the purple thorax, but they have a brown puparium. So usually when the phenotype of the non-recombinant progeny is at the same as phenotype of the parents, so the phenotype of non-recombinant progeny is at the same as phenotype of the parents like this. In this case, we call it as the cis configuration. Okay. This is the in this slide we will learn another concept allele in the repulsion configuration. So, okay. So repulsion configuration, we call it as a trans configuration. So wild type and mutant allele are found on the same chromosome. The wild type and mutant allele are found in the same chromosome. Okay, so in these cases, they are heterozygote each other, and also the phenotype is the green thorax and brown puparium. So when they cross with the when they did test crosses, okay, so during the gamete formation, so P plus small b and small p and small b plus is non-recombinant gamete. And how about after they crosses P plus B plus and also P B like this? This is recombinant gamete. So after the fertilization, so usually the non-recombinant gamete are predominate. Okay, in these cases, the phenotype. Okay, in these cases, the phenotype is green thorax, but they will show the black puparium. So in these cases, they show that purple thorax, but they will have the brown puparium. Okay, how about the recombinant progeny? So recombinant progeny is like this. So after recombination happens like this. The P plus B plus is the dominant, then small p and small b. So the phenotype is green thorax and brown puparium. How about this one? This one is small p, small b, small p, small b, purple thorax and black porphyrium. So when the phenotype of the recombinant progeny is the same as the phenotype of parents, this phenotype is the same as the parents. In this case, we call it as they are in trans configuration. So usually the arrangement, coupling or repulsion of the linked gene on the chromosome affect the result of test crosses. Okay, the result of test crosses usually when the phenotype of a non-recombinant progeny is the same as the phenotype of a parent, we call it as cis configuration. After the test crosses, when the phenotype of recombinant progeny is the same as phenotype of parents, we call it as the trans configuration. This is concept check 2. Okay, the question was the following test crosses produces the progeny. So this is the heterozygote, large A, small a, large B, small b, and they did test crosses with the small a and small bb. And the progeny, the number of progeny is like this. So this is the, for example, if there is the no linkage, means that the ratio between this one will be the 1 to 1 to 1 to 1. But the ratio is not 1 to 1 to 1 to 1. It means that the gene between A and B, they are linked to each other. Okay, so now we want to, the question was what the gene in the A and large A, small a, large B, small b parents in coupling or repulsion. Okay. So in the, for example, we already learned that in coupling configuration, the phenotype of the non-recombinant progeny is exactly same as the parent phenotype. Okay. How about the in these cases? So this is in this case is this is 40 is the non-recombinant progeny because usually the non-recombinant progeny is predominate. So this means that the phenotype of the non-recombinant is different from the phenotype of the parents. So it means that this is the trans configuration. They are the gene is in the trans configuration. Is a repulsion. They are in alleles in the repulsion configuration because the phenotype of the recombinant. So the number is small, so means that this is the recombinant. So phenotype of recombinant is the same as phenotype of the parents. In this case, the genes are in the repulsion or trans configuration. So what is percent recombination between A and B? Okay, so this is a non-recombinant progeny, and this is non-recombinant progeny. So the percent recombination means that 10 to 10 per 10 to 10 plus 40 plus 40 plus 10 means that the recombination frequency is 20%. Okay. This is table 7.1, result of test cross with a complete linkage or independent assessment and linkage with some crossover. So if they are in independent assessment, so this ratio will be the 1 to 1 to 1 to 1. So if they are in complete linkage, so they only show the non-recombinant progeny, and also the ratio will be 50 and 50. So this is the linkage with some crossover. So it means that non-recombinant progeny will show that more than 50%. So this is non-recombinant, and this is also non-recombinant. But how about the recombinant progeny? Is the percentage will be the less than 50%. In this slide, I will explain how to predict the outcome of crosses with a linked gene. So usually the recombination frequency allows us to predict the expected offspring with the linked gene. Okay, so usually, for example, in these cases, this is cucumber. This case is show that warty and 덜 fruit means that warty means that 울퉁불퉁 and 덜 means that 무광택. So the gene which encode the warty and the gene which encode the 덜 is located in the same chromosome like this. So we did test crosses. So this is the heterozygote and cross with the recessive homozygous. So, for example, geneticists have determined that the recombination frequency between two genes in cucumber is 16%. So this is recombination frequency is 16%, means that the predicted frequency of a gamete, the recombinant the gamete and recombinant gamete will be the 0.08 and the 0.08. And also the predicted frequency of the non-recombinant gamete will be 0.42 and 0.42 like this. So usually the predicted frequency of a progeny, is obtained by multiplying the frequency of the gamete. So, okay, so from this one, so usually the gamete will have small t and small d. So this is a non-recombinant gamete. The ratio, the predicted frequency is 1. So usually the predicted frequency of progeny is multiplied of this one and this one, and this one and this one, and this one and this one, and this one and this one like this. So they will have the this one. This is predicted frequency of a progeny is 0.42 and also 0.42. This is the non-recombinant progeny. How about this one? This is a recombinant progeny. Is the predicted frequency is 0.08 and 0.08. In this slide, I will explain how to test for independent assessment. So in this time, we will use chi-square test of independence. This chi-square test of independence determines if two genes are sorting independently or not. The basic principle of chi-square test of independence is based on the chi-square goodness of fit. All of them is nearly exactly similar, except for to make the contingency table. So, okay, so this is this is crosses, also test the crosses. So we will do test for the independent assessment, okay? So this is the cockroaches. In Korean, we call it as the 바퀴벌레. So this is the heterozygous. The body is the brown body, and they have the straight wings like this. Another recessive homozygous. This is the small YY and small CB. And this is the yellow body, and they show the curved wings. So brown body is dominant than the yellow body, and straight wing is also dominant than curved wings like this. So after test crosses, okay, so test crosses carried out between the cockroaches, and they show that different the offsprings, different number of offsprings. So if the number is the 1, 2, 1, 2, 1, 2, 1, means that this is there is no linkage, and it means that they sort independently. But the ratio is different, not 1, 2, 1, 2, 1. So maybe you can say that this is not, maybe this not follow independent. Maybe the two genes are located in different chromosomes, but we will not know exactly, not yet, okay? So after that, we have to make the contingency table. So this is contingency table. So we have to construct a table to observe the number of progeny. Okay? First one is to test for independent assessment of allele encoding two traits. A table should be constructed. Okay? For example, Y. For example, this Y plus can be crossed with a small y and y plus y. How about this one? This small y can cross with a small y like this. Okay. How about the CB, the wing, the genotype wing? So one can cross with CB plus CB, and another one CB plus CB like this. Okay, after that, so this is the one genotype, and this is also the other genotype. After that, we have to add a number. For example, y plus y and cb plus cb, number is 63. How about y plus y and cb, this one is 28. How about yy, cb plus cb, number is 33. How about small yy, small cb and cb is 77. After that, we have to compute the total for each row. 63 plus 33, 96, and 28 plus 77, 105. And also we have to calculate the total per column. 63 plus 28, 91. 33 plus 77 is 110. And also we have to compute the grand total. Grand total is 201. It's like this. After that, we have to make the expected number. So expected number. So before we calculate the expected number, we have the assumption. We have the assumption. Assumption is that segregation of the allele and one locus is independent of the segregation of allele at the other locus. So previously we learned that how to calculate the predicted frequency of progeny. Okay, the predicted frequency of progeny is obtained by multiplying the frequency of the gamete like this. So we have to calculate the frequency of each gamete, and after that we have to calculate, multiply with another frequency. It's like this. So that's why we have this ratio like this. Okay, so to get the expected number, first we have to multiply with the grand total, and after that we have to calculate the frequency of this gamete. Okay, frequency of this gamete is based on the total grand total number per 91. How about in this row? And also this is the CB plus CB. The frequency will be the total grand total number per this 96. After that, so this is so finally the expected number will be the row total multiply column total per grand total is like this. Okay, so first we have to calculate the expected number. So this is the number observed: 63 and 28, 33 and 77. And also we have to calculate the number expected. So number expected means that this one, y plus y and cb plus cb. So y plus y and cb plus cb is that grand total is 201. And also after that row total is 96, and the column total is 91. So this is the expected number. How about this one? Y plus Y and CB plus CB, like this one, okay? The expected number is grand total 201, and also the row total is 105, and the column total is 91. So the expected number is like this. How about this one? YY, small YY, CB plus CB, this one. So this is the grand total is 201, and the row total is 96, and also a column total is 110. And this is expected number. After that, this one. How about this one? Small YY and CB is this one is that the grand total is 201, and the row total is the 105, and the column total is 110. Is the number is like this. So, and also so means that the expected number of progeny is assuming that independent assessment are calculated like this. So we can assume that the independent assessment, after that we have to calculate the expected number of progeny. So this is expected number. So expected number is the row total multiply column total per grand total is like this. After that, we have to calculate this one. So we have to calculate the chi-square value. So chi-square value, we already learned it previously. So this is chi-square value. So this is the observed number, 63 minus expected is 43.46, and multiply divided by expected number 43.46. So we have to calculate all of them like this. So the chi-square value is the 30.73 is like this. Except that we have to calculate number of freedom. Number of freedom is the df is we can get like this. Okay, this is chi-square value is calculated. After that, okay, this is the number of freedom. Number of freedom is calculated by based on number of rows. Number of rows is the how many rows. In the next, we have to calculate a chi-square's value. So we already know that how to calculate a chi-square values. So this is the how to calculate chi-square values. So this is the expected number. This is number of observed, and this is number of expected. So for example, in these cases, 63 minus 43.46. After that, we can do square and divided by expected number is 43.46 like this. So we have to calculate chi-square value. So chi-square value is 30.73 like this. Okay. After that, we have to determine the number of freedom. Number of freedom is calculated by based on number of row. How many number of row? 1 and 2. 2 minus 1 multiply number of column. How many column? 1 and 2. 2 minus 1. So this is the we have to calculate the number of freedom. So number of freedom is 1. Okay. Next, so the number of freedom is 1, and the chi-square value is located maybe here. Here means that this means that P is less than 0.005. So if the probability is P is less than 0.05, means that chance is not responsible for the difference. So means that the gene for body color and the type of the wing are not sourced independently. They must be linked. So this is the conclusion. So based on and we have to calculate. So once again, we calculate the chi-square value, and also we determine the number of freedom. Number of freedom is 1. Okay, so the chi-square value is located here. Means that the probability is less than 0.005. It means that if the probability of chance is less than 0.05, means that chance is not responsible for difference. It means that the gene for body color and the gene for type of wing does not assert independently. Are not assert independently. Must be linked. It's like this. In this slide, I will explain how to construct the genetic map. So genetic map, we can construct the genetic map based on the recombinant frequency. For example, in these cases, so A and B they are linked to each other, and the distance between A and B is far away from here. So for example, in these cases, recombination happens here, 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 here. Okay? When the distance between A and B is very close to each other, maybe recombination happened here, here. And so it means that recombination frequency is higher, in this case, higher than this one. So usually the genetic maps are determined by recombinant frequency. So for example, in these cases, the A and B is the recombination. The genetic map is the map unit is that mu is the centimorgan. So Morgan found this one, so we call it as centimorgan or as mu. For example, the distance between A and B is 5 mu, means that the recombination frequency is 5%. How about the B and C? The B and C is the recombinant frequency is the 10 mu, means that 10%. Okay, based on this recombination frequency, we can calculate the distance between A and C. A and C will be the 15 m unit. Okay, so this is exactly the same as this one. Okay. Okay, so based on so this is the how we construct the gene mapping. Okay, for example, the gene A and D pair, the recombination frequency is 8%, and B and D is 13%, and C and D is 23%. So based on this frequency, we have to construct genetic maps. For example, we start from the highest frequency, 23%. So maybe in D and C will be in the outside. Okay, for example, and A and D will be the 8%. Maybe A and D will be the 8 m unit. How about the B and D is the 13%, means that B will be located here. This is B and D is 13. Okay, also, so based on this recombination frequency, we can calculate the D and C is in the outside, and the A and B is inside. The distance between A and D is 8 m unit, and the distance between the A and B will be the 5 m unit. and the distance between B and C will be the 10 m unit. It's like this. Okay. In this slide, we will explain one exceptional cases in the genetic mapping. Okay. Usually, if there is only one crossover happens, so this is the non-recombinant, and this is the non-recombinant, and this is the recombinant. Based on the number, we can calculate the recombination frequency. After that, we can construct a genetic mapping, but sometimes some exceptional cases can happen. For example, so single crossover will switch the allele, but another second crossover will reverse the effect of the first. So finally, they will produce only non-recombinant gamete. For example, large A, large B, large A, large B, and small a, small b, small a, small b. Even though the two double strand crossover happens, they only produced non-recombinant gamete. Okay, so it means that our double strand, two strand double crossover, double crossover between two linked genes A and B produces only non-recombinant gamete. So it means that it can induce underestimation of the true map distance. So usually the genetic map based on the short distance are usually more accurate than the long distance, because usually in long distance, usually the double crossover, two-strand double crossover sometimes happen. But if the distance is very short, usually the chance to have two-strand double crossover is very low. So the genetic map based on short distance are more accurate, but genetic map based on the long distance is not accurate. A little bit is not 100% accurate. In this slide, I will show how to construct the genetic mapping in more details. So 2-point test crosses means that crosses between two genes. So usually we use the 2-point test crosses when we construct our genetic mapping. Okay. For example, in these cases, between gene A and B is the recombination frequency is 50%. It means that, so we already learned in the 7.1. So if the gene is located in different chromosomes, they will also independently, so 50% they will have the non-recombinant gamete, and 50% they will have the recombinant gamete. So in this case, when the recombination frequency is 50%, means that it follows the independent assortment. It means that this two gene is located in the different chromosome. Okay, for example, gene A and B, the recombination frequency is 50%. It means that gene A and gene B is located in different chromosomes. How about A and C? A and C is also 50%, means that A and C will be located in the different chromosomes. How about A and D? A and D means that also 50%, means that A and D will be located in the different chromosomes. Okay. How about when we cross with B and C? B and C is the 20%, means that B and C is located on the same chromosome. How about B and D? B and D is the recombination frequency is 10%, means that they are also located in the same chromosome. How about C and D? C and D is 28%, means that C and D is also located at the same chromosome. So so we can, based on this information, so we can write down here at another chromosome, maybe the A will be located here, and another different chromosome, B and C and D will located at the same chromosome. Okay? So between B and C is 20 M unit, and between the B and D is 10 M unit, but in the C and D is the recombination frequency was 28. It means that because the C and D is too far away from, so it means that there happens underestimation of true map distance happen because there is the double crossover happen between C and D. That's why the recombination frequency was the 28%. So actual distance will be the 30 M unit like this, okay? Because between C and D, it means that the double crossover is happens, okay? In this slide, we will learn the 3-point test crosses. So usually the also 3-point test crosses also can be used to map 3 linked genes. Previously, we only used the 2-point test crosses, means that 2-point test crosses means that crosses between 2 genes. Now we will think about the 3-point test crosses between the 3 linked genes. So usually in the 3 linked loci, usually 3 types of crossover happen. For example, this is centromere, this is centromere, this is pairs of homologous chromosomes. They are composed of the gene A, gene B, gene C. And 3 genes is linked each other. Okay? So this is a large A, large B, large C, and this is a large A, large B, large C. On another chromosome, they have small a, small b, small c, and small a, small b, small c. So usually in this case usually between A and B, there is only one single crossover can happen, or between B and C, there will be another single crossover can happen. Or between A and B, single crossover happen. In addition, and between B and C, additional a single crossover can happen. So in this case, is usually finally the double crossover happens. So usually the 2 types of single crossover, and also there is another double crossovers can be happens. So in each case is when the one single crossover happens between A and B, so one gamete will have the non-recombinant A, large B, large C, and the other one, they also have a non-recombinant small a, small b, and small c. But inside, we will have a recombinant gamete, large A, small b, and small c, and small a, large b, large c. So this is when single crossover happen between the A and B, the gamete will be like this. How about when the single crossover happen between B and C? Okay, so 2 gametes will show that non-recombinant. We'll have a large A, large B, large C. We'll have the small a, small b, small c. But inside, the 2 gametes have the recombinant. Large A, large B, small c, small a, small b, large c. But when the double crossover happens, so they will have the 2 is non-recombinant, 2 is the recombinant. In any cases, the two of the resulting chromosomes are recombinant and two are non-recombinant. But we have to think about in double crossover. So in double crossover, so recombination chromosome resulting from double crossover have only the middle gene altered. For example, in these cases, this is non-recombinant, non-recombinant, this is recombinant, and recombinant. When double crossover happen, only middle gene is altered because large B can go to the here and small b is go to the here. So when double crossover happen, so only the middle gene is altered. So you have to memorize this one, okay? In this slide, we will show how to construct a genetic map with 3-point test crosses. Okay, so this is test crosses. This is the recessive homozygous. Okay, and this is the wild type and also heterozygote like this. Before we go further, we have to know the gene type. Okay, for example, in fruit flies, if the eye color is very bright red color, this is the scarlet. So we call it as scarlet. But the wild type is dominant than the scarlet. The ST plus is the dominant than scarlet ST. Okay. How about the body color? So this is wild type body color, and this is the ebony type wild color. Ebony body is the body color is very black, it's like this. And this is the dominant, wild type is dominant than the ebony color. So E plus is dominant than the ebony color, small e. And also, how about the body blister? For example, the fruit fly, they body, they have a blister, they have tall blister, they have body hair. So this is the wild type hair, looks like this, and this is the spinless. It means that very small, and usually the wild type they have large pore hair, but spinless sometimes they have three. Also they have the very small hair. But wild type is the dominant than spineless. So SS plus is the spineless and wild type, and SS is the spinless. Okay. Okay. So we did the test crosses with the 3-point test crosses. After that, we have this kind of progeny number. The wild type we have the 283, and all mutant we have 278, and also we have several different progeny phenotypes like this. So now, based on this data, I will show you how to determine the gene order. Okay. This slide, I will show the steps in determining gene order in the 3-point test crosses. So this is the 3-point test crosses. We already mentioned the previous slide, but we don't know the order. But now I will show you how to determine the gene order in 3-point crosses. Okay. The first one is we have to identify the non-recombinant progeny, two most numerous phenotype. So it means that the most numerous phenotype is this one, 283 and 278. And so this is the wild type, and also they show them the all mutant, okay, like this. So this two is the non-recombinant. Next, we have to identify double crossover progeny. Okay, because the double crossover, if the double crossover happens, the progeny will be very rare. So we have to identify two at least numerous phenotype. So we find that 5 and 3 is two least number of phenotypes. So this is maybe the double crossover progeny. Okay, so now we have to compare the phenotype of the double crossover with the phenotype of non-recombinant progeny. So for example, so when we compare this one and this one, okay, so two will show the same phenotype and one will show the different phenotype. How about we compare with this one and this one? Two will show the same phenotype and one will show different phenotype. So it means that the characteristics that differ between the double crossover and the non-recombinant progeny is encoded by the middle gene. Okay, so what is difference? Difference is spineless, isn't it? Spineless, isn't it? So when we compare this one, the spineless is different. And also when we compare all mutant with the scarlet and ebony, the spineless is different. So it means that spineless is located in the middle. Okay? Not ebony is located in the middle. The spineless is located in the middle. Okay. In the previous slide, we find that spineless is middle gene and spineless is middle gene. Okay. So next the spineless gene, there will be scarlet and there will be ebony. And next to the scarlet, spineless, there will be scarlet and there will be the ebonies like this. So next we have to find the position of crossover. Now we have to find the position of crossover. For example, if the single crossover happens here, they will have this kind of the gamete. Or when the single crossover happens between here, the gamete will be like this. Okay. So when we compare with the non-recombinant progeny, for example, this one is when you compare it with this one only have the one phenotype is different. The different phenotype is the scarlet. How about when we compare with this one and the wild type, only different one is scarlet. So it means that between the scarlet and the spineless, there was a single crossover. How about these cases? When we compared with this ebony with the wild type, only ebony is the difference. So when we compare with this one and this one, so only ebony is difference. Means that the crossover happened between the spineless and the ebonies like this. Okay. So next, the important thing. So we have to find the location, position of crossover. So based on the phenotype. Okay. Next, we have to calculate the recombination frequency. So how about the ST-SS recombination frequency? The total is the 755. Okay, so means that ST-SS means that the recombinant will be the 50 and 52 and 5 and 3. And this slide, we will show the last step when we construct a genetic mapping with a 3-point test process. So finally, we have to determine the location of a double crossover again. So this is the double crossover. So maybe between here and here and here and here, maybe the double crossovers happen. Finally, we have to calculate the recombination frequency. The recombination frequency is the total number and the sum of all single and double crossover. Okay. So between in ST and SS, okay, total progeny is 775, and because between here and there was the single crossover, so means that the, the single crossover, they will have 50. So between this one, they will have the single crossover, so maybe this one will be the 52, and this is double crossover, and also between here and here, there was also some single crossover, so it means that 5 and 3. So the recombination frequency between S and ST and SS will be the 14.6 point. How about the recombination frequency between SS, and E? The total number is 755. Okay, so how about between the SS and E? And this number is 43, and about this one is also number is 41, and also double crossover this one, the 5 and 3, so the frequency will be the 12.2%. So this is the final the mapping. So SS is located in the middle, and between the distance between the SS and the ST will be the 14.6 mu, and also between SS and E will be the 12.2 mu. So finally, based on this calculation, the distance between the ST and E will be the 26.8 mu. It's like this. In this slide, I will explain how to calculate coefficient of coincidence. It means that coincidence means that the double crossover happens. So, okay, the coefficient of coincidence means that number of observed double crossover is divided by number of expected crossover. So number of observed double crossover is 5 plus 3, and number of expected double crossover is we already learned from here, and total number is 755, and the number the recombination frequency between the ST and the SS is 0.14%, so multiplied 0.14.6, and the recombination frequency between the ST and E is about 12.2%, means that 0.122, so means that the number of expected crossover will be the 13.4. So the coefficient of coincidence will be the 0.6. So this is the coefficient of coincidence. And I also want to introduce how to calculate interference. Interference means that the degree to which one crossover interferes with additional crossover. So interference means that in Korean we call it as 방해. 방해 means that the degrees to which if the one crossover happens, it interferes with additional crossover. So this is interference. Interference is the 1 minus coefficient of coincidence. So in these cases, the interference is that 1 minus 0.6 will be the 0.4 will be the interference. Okay. So in this slide, we will solve the concept check 3. The question is that 3-point test crosses carried out between 3 linked genes. The resulting non-recombinant progenies are S plus, R plus, C plus, and SRC. And the double crossover progeny are S, R, C plus and S plus R plus C. So which is the middle locus? So which is the middle locus? Okay. First we have to check. Okay. First we have to identify non-recombinant progeny, and also we have to identify double crossover progeny. And we have to compare the difference between the double crossover and the non-recombinant progeny. So this is the non-recombinant progeny, S plus R plus C plus SRC. And this is the double crossover, S plus R plus C and SRC plus. If you see the difference between the non-recombinant progeny and double crossover progeny is C. So it means that C is the middle locus. Okay? I will explain the linkage group in the Drosophila. Because Drosophila has 4 pairs of chromosomes. For example, the female, they have chromosome 1 is XX, and the male, they have a chromosome 1 is XY, and they also have a chromosome 2 and chromosome 3 and chromosome 4. Because they have the 4 pairs of chromosomes, they have the 4 linkage group. In chromosome 1, there are several kinds of genes is located in chromosome 1. They are linked each other. In chromosome 2 is also there are several genes is located in chromosome 2, and chromosome 3 also there are several genes is located in chromosome 3, and chromosome 4 is very small. But even though they are very small, there are several genes is located in chromosome 4. So these genes are mapped using the recombination frequency. And also small chromosome 4, because chromosome 4 is very small like this. So usually the chromosome 4 never undergoes recombination. The important thing in this slide is that the gene in the chromosome 1 and chromosome 2 and chromosome 3 is mapped using the recombination frequency. Okay. In this slide, we will see the effect of the multiple crossover. So usually the double crossover takes place between only two of 4 chromatids. So in this case, initially they had large A, large B, and large A, large B, and small a, small b, small a, small b. Even after double crossover happens, the genotype will be the large A, large B, large A, large B, small a, small b, small a, small b. So in these cases, we cannot detect the recombinant. But sometimes double crossover happens in the 3-strand in 3-strand like this, or the 3-strand like this. Or sometimes double crossover happens in the 4-strand like this. Okay, when the double crossover happened in 3-strand, okay, so initially it was large A, large B, large A, large B, small a, small b, small a, small b, but the genotype after 3-strand double crossover, large A, large B, and small a, small b. But large A, small b, small a, large b. So it means that 50% is non-recombinant and 50% is recombinant. Okay, we can detect we can detect the 50% detectable recombinant. We will have the 50% detectable recombinant. But in these cases, which one? The first one is large A, small b, large A, large b, small a, large b, small a, small b. It means that 50% is non-recombinant and 50% is recombinant. How about the 4-strand double crossover? So initially it was A, large B, large A, large B, small a, small b, small a, small b. So after that, the final genotype will be the large A, small b, large A, small b, small a, large b, small a, large b. So it means that all of them 100% is recombinant. So, but all type of double crossover produce an average of this case is 0%, this case is the 50%, and this case is 50%, and this case is 100%. The average is the 50% is the average detectable recombinant. Okay. In this slide, we will see the effect of 2-strand double crossover and the effect of 3-strand double crossover again. So if there is a 2-strand double crossover happens, we cannot detect the recombinant. But when there is the 3-strand double crossover happens, we can detect the recombinant. There is the recombinant progenies, like the 50% and 50%. However, the progeny are the same type as those produced by single crossover. So the progeny is exactly same as the same type as those produced by single crossover, like this. For example, they have large A, large B, small a, small b, and they also have large A, small b, small a, large b. Like this, in single crossover, they will have large A, large B, small a, small b, and large A, small b, small a, large b, like this. So even after 3-strand double crossover happens, the progeny is at the same type as those produced by single crossover. So this is the 2-strand double crossover, no recombinant progeny, but even after the 3-strand double crossover, we have the recombinant. But this progeny is at the same type as those produced by single crossover. In this slide, I will explain the mapping function. Okay, so as the distance between the two genes increase, usually the multiple crossover takes place. But in these cases, even after double crossover happens, so we cannot detect the recombination. So it means that there will be the discrepancy between genetic distance and the physical distance. So it means that it can induce underestimation of true map distance. For example, the actual map distance is the 40 mu, but the recombination frequency is around 30%. For example, around 10% we cannot detect the recombination. So to correct for this discrepancy, geneticists have developed mathematical mapping function. So for example, recombination frequency is around 30%. The actual mapping distance will be the 40%, which is like this. So once again, to correct this discrepancy, geneticists have developed mathematical mapping function like this. So when they calculate when they observe the recombination frequency is about 30%, the actual distance will be the 40 mu, is like this. Okay. In this slide, I will explain the deletion mapping. So deletion mapping can determine the chromosomal location of gene. So there is two cases. One case is our gene of interest, small a plus. Our gene of interest is located in the deletion region. Another case is our gene of interest is not within the deletion region. So in this case, usually the individuals homozygous for recessive mutation, small a, small a, small a, small a is crossed with individual heterozygous for deletion. So one has deletion, one has deletion. But when the gene of interest is located within the deletion region, so after crosses, this is the F1 generation. F1 generation will be this is A plus A, means that this phenotype will be the wild type. How about in these cases, small a and there is no gene of interest? It means that it will become the A mutant. Or in the case of the gene of interest is not within the deletion region, after crosses, this one will become the A plus A, and also this one also will become the A plus A. So both of them will show the wild type. So if they show the 50% is wild type and 50% is mutant, it means that our gene of interest is located in deletion region. If they show that 100% wild type, means that our gene of interest is not within the deletion region. In this slide, I will explain another physical chromosomal mapping through molecular analysis. Previously, we learned that the deletion mapping is one method of the physical mapping method. And another method nowadays people usually use fluorescent in situ hybridization. So it means that it can determine the chromosomal location of gene. So this is the example. So during my PhD, I also did fluorescent in situ hybridization. For example, this is chromosomal 19. I found it. I tagged the green color in chromosomal 19, and I also tagged the NOTCH3 gene as the red color. So in the non-cancer region, we will see that the ratio between green and the red is nearly similar to each other. But in cancer, ovarian cancer patient, we will see that the ratio between the green and the red is different. So okay, this is one example of my research, but the fluorescence in situ hybridization is determining the chromosomal location of gene. For example, we tag the reference region of the chromosome with green, and also we also tag our gene of interest with a different color. It's like this. So this is another method of the physical chromosomal mapping. Nowadays, people usually use fluorescent in situ hybridization, like this. So in this slide, we see the final subject. The recombination rate exhibit extensive variation. So level of recombination rate varies widely among species. The recombination rate is different in for example, mouse and human is different. And also level of recombination rate is different among chromosomes of a single species. For example, in our human, the recombination rate in chromosome 1 and the recombination rate in chromosome 2 is different. and also level of recombination varies between the male and female. And there is also recombination hotspot. This recombination hotspot means that recombination rate is at least 10 times as high as the average elsewhere in the genome. So usually the human genome contains about 25,000 to 50,000 hotspots. So I also found some hotspot in the cancer. The region is PAM19A. So usually the cancer patient have a lot of the recombination hotspot. In this chapter 7, we learned linkage and the recombination and the gene mapping. Okay, so we learned the linked gene in subject 1 and 2. We also learned the 3-point test crosses, and we also learned the physical mapping method, and also finally we learned the recombination rate exhibit extensive variation. So today we will finish the class. Okay, thank you.